So this is a lecture on gas laws, and these are the main component of Chapter 11. So we're going to start with the nature of gases and the assumption that they don't always obey all the assumptions made by the kinetic molecular theory. The kinetic molecular theory basically says that gases are very small, they move around all the time, they don't really collide with each other. But what we're going to do now is calculations that look at four main properties of gases and how they change. So the four properties are number of gas particles, which you can think of as moles of gas, temperature, pressure, and volume. So all four of those properties work together to affect how a gas behaves, and when you change one, the other three are automatically affected. So the first law we're going to look at is Boyle's law. His law, Boyle is a person, that's why it's capital B, states that the volume of a gas at a constant temp is inversely proportional with pressure. With all three of these gas laws we're going to talk about today, the number of moles of gas, N, the amount of gas is going to stay constant. So with Boyle's law, pressure is also constant, meaning it stays the same. So the only two variables changing with Boyle's law are pressure and volume. And what he says is they're inversely proportional or opposite. So as pressure goes up, volume goes down, and vice versa. So you see the equation here is P1V1, which is the initial set of conditions, equals P2V2. And what you're going to do is you're going to get three of those four variables in a problem and then solve for the fourth one. So this picture kind of just shows Boyle's law in action. You see when you have a plunger and the pressure is very high, the volume is very low. And when the pressure is low, the volume's high. So they are opposite. They're inversely proportional. If you were to graph pressure versus volume, it's going to be an inverse graph, meaning it's going to be a downward curve. Remember, they are opposite. So you see here is a real life example of a Boyle's law problem where you're taking the pressure and the volumes. As you change the pressure, the volume changes as well. So a sample problem, number one, a sample of helium in a balloon is compressed from 4 liters to 2.5 liters at a constant temp. So you see the volume changes from 4 to 2.5. If the pressure of the gas in the 4-liter volume is 210 kPa, what will the pressure be at 2.5? So notice I have my initial volume, my second volume, and then when I read the second part, it says if the pressure in the 4-liter is 210. So your number here for the 4-liter needs to match your pressure. So 4 liters V1, 210 has to be P1. And again, the units can be anything as long as they're the same. So you see the volume's in the same unit, pressure's in the same unit, plug it into my equation, P1V1 equals P2V2, and then simply solve for P2. Next law is Charles' law. In his law, the pressure is now constant. So again, the number of moles of gas and pressure is constant. And his law says the volume of a gas is directly proportional to its Kelvin temperature. So directly proportional means it's the same. So unlike Boyle's law, as the volume goes up, temperature goes up. As volume goes down, temperature goes down. And notice it says Kelvin temperature. We've talked about that a lot. Kelvin has to do with absolute zero. The way you convert from Celsius to Kelvin is you simply add 273. And for all gas law problems, your temperature has to be in Kelvin. The equation is there. V1 over T1 equals V2 over T2. And again, the 1s are the initial, the 2s are the new. So a plot of Kelvin temperature and volume, because it's directly proportional, is going to be just a direct straight line. As one goes up, the other goes up. And you can see here from the actual graph that the line is the same. So sample problem number 2, a gas sample at 40 degrees occupies a volume of 2.32 liters. If the temperature is changed to 75 degrees, what will the new volume be, assuming the pressure remains constant? So notice I have my T1 given in the problem, my V1, and then my T2, the change, and I'm looking for the V2. Notice for the temperature, that whole rule of it's okay as long as they're the same doesn't apply. They have to be in Kelvin, and you simply just add 273. So 40 plus 273, and then 75 plus 273. Very simple. Plug it into my equation, V1 over T1 equals V2 T2. And remember, when you have an equation set up like this, you do opposites. So you cross multiply. So you're going to do 2.32 times 348, and then 313 times V2, and then solve. And you get 2.58 liters. Last law is Gay-Lussac's law, sometimes the GL law. It's actually two people came up with this. It states now that the volume is constant, so volume and number of moles of gas are constant, and that the pressure varies directly with the Kelvin temperature. So pressure and temperature now vary directly, meaning they vary the same. So as pressure goes up, temperature goes up. As pressure goes down, temperature goes down. You see the equation is very similar to Charles' law. Instead of volume, you have pressure. So again, the graph looks very similar to Charles' law because it's the same. They're directly related. As one goes up, the other goes up, etc. And you see here from a real-world example showing the pressure and temperature difference. So the pressure of a gas in a tank is 3.2 atm at 22 degrees Celsius. If the temperature rises to 60 degrees, what will be the gas pressure in the tank? So I have my P1 there, and then notice my T1 and T2 are in Celsius, given in Celsius, which they normally will be. Add 273 to turn them both to Kelvin. You have to do that for all temperatures. And then you're looking for the P2, simply plugging in here, and I'm cross-multiplying to solve, and I get a P2 of 3.61 atm.